Measure phase. Process capability. Full detailed content with examples, definitions, stories, exercises. 1. What is process capability? Definition. Process capability is a statistical measure of a process's ability to produce outputs that meet customer specifications consistently. It quantifies how well a process performs relative to the set specification limits. Example: manufacturing. A factory produces piston rods that must be between 9.8 millimeters and 10.2 millimeters. Process capability measures if the rods consistently fall inside that range. Services. A bank aims to approve loans between 2 to 5 days. Capability measures if loan approvals happen consistently within this window. Story. Imagine you run a pizza delivery business. You promise customers delivery within 30 minutes. If you consistently deliver between 25 to 30 minutes, your process capability is good. If you sometimes deliver in 20 minutes and sometimes in 1 hour, your capability is poor, even if the average delivery time is close to 30 minutes. Second, process. Stability versus process capability. Definition. Process stability means the process operates predictably over time without sudden special cause variations. Only stable processes can have their capability measured reliably. Example: manufacturing. A machine that produces consistent dimensions every day, stable. Services. A hospital emergency room where patient wait times are steady at 20 to 30 minutes, stable. If wait times vary wildly, 10 minutes one day, 2 hours next day, unstable. Story. Imagine a restaurant has food preparation times that are highly unpredictable. Some days it's 10 minutes, other days 40 minutes. Would you say the restaurant is reliable? Number. That's why stability comes before capability. Exercise 1. Given. Sample shaft diameters over 30 days. Task: create an X-bar chart and determine if the process is stable. 3. Recap of normal distribution. Definition. A normal distribution is a bell-shaped symmetrical curve where most values cluster around the mean. Key properties: 68% data within plus or minus 1 sigma, 95% within plus or minus 2 sigma, 99.7% within plus or minus 3 sigma. Example: manufacturing. Thickness of steel sheets following a bell curve around 2 millimeters. Services. Call center, call handling times clustering around 5 minutes. Story. Imagine you throw darts at a dartboard. If your darts are grouped tightly around the bullseye, that's like a normal distribution. Tight, centered, predictable. Exercise 2. Task: plot a histogram in Minitab for delivery times and overlay a normal curve. Fourth, process capability ratios. Concept. Definition. Capability ratios compare the spread of the process output to the range allowed by customer specifications. CP measures potential capability, spread only. CPK measures actual capability, spread and centering. Example: manufacturing. Rod length, spec, 100 plus or minus 2 millimeters. Small spread, high CP services. Support ticket closure time spec, 2 to 6 hours. If closure times vary widely, 1 to 8 hours, low CP. Imagine you have a dog and a fence. CP measures if your dog's roaming range fits inside the fence. CPK checks if the dog stays close to the center of the backyard, not hugging the fence edges. 5. Understanding specification limits. Definition: lower specification limit, LSL, the minimum acceptable limit. Upper specification limit, USL. The maximum acceptable limit. Example, process, milk bottling, call response time, help desk, LSL, 980 milliliters, 0 minutes, USL, 1020 milliliters, 2 minutes. Imagine, your airline promises baggage delivery within 15 to 30 minutes. Less than 15 minutes equals rare, LSL. More than 30 minutes equals bad service, USL. Exercise 3. Task. Define LSL and USL for an ATM cash dispensing time. 6. The Z-score and sigma level. Definition. The Z-score tells how far a point is from the mean, measured in standard deviations. Formula. Z equals X minus M divided by S. Example. Services. Average chat response time equals 3 minutes. Standard deviation equals 0.5 minutes. Response time equals 4 minutes. Z equals 4 minus 30. 0.5 equals 2. Z equals the fraction. 4 minus 3 over 0.5 equals 2. Z equals 0.5. 4 minus 3 over 0.5 equals 2. 2 sigma above mean. Imagine, a basketball player's height is 6 feet. In a population where average height is 5 feet 7 inches and standard deviation equals 3 inches, Z equals open parenthesis 6 feet, 0 inches, minus 5 feet, 7 inches. Close parenthesis divided by 3 inches equals 5/3, approximately 1.67 above average. Exercise 4. Task. Calculate Z-score for delivery times in sample data. 7. Calculation of DPMO. Definition. DPMO. Defects per million opportunities. Calculates defects considering how many opportunities exist for defects. Formula. DPMO equals open parenthesis. Defects over opportunities close parenthesis times 1 million. Example. 3 defects found in 500 customer interactions. 1 opportunity per interaction. DPMO equals 35,000 times 1 million equals 60,000. DPMO equals left parenthesis 3 over 500. Right parenthesis times 1 million equals 6,000. DPMO equals 5,000. 3 times 1 million equals 6,000. Imagine, you send 1,000 online orders a day. If 5 are wrong, your defect rate is 0.5%. But DPMO helps standardize this as how many per million for easier benchmarking. Exercise 4. Task. Calculate DPMO for given service center defect data. 8. Short-term versus long-term capability. Aspect. Focus. Data used. CP/CPK, short-term. Immediate controlled environment. Small study data, PP/PPK, long-term. Real-world daily variability. Full operational data. Example. Project team measures. Ticket closure time during a pilot project, CP/CPK. Production monitoring. After 6 months, shows long-term performance PP per PPK. Imagine, you clean your room perfectly today. Looks great, CP/CPK. But if in 2 months it's messy again, your long-term performance, PP/PPK, is poor. Process capability ratios help us measure how well a process meets specification limits. CP measures potential capability, assuming the process is centered. CPK adjusts for how centered the process actually is. PP and PPK are similar, but use overall long-term variability. Formulas: CP equals USL minus LSL divided by 6 sigma. CPK equals minimum of USL minus MU divided by 3 sigma. Mu minus LSL divided by 3 sigma PP equals USL minus LSL divided by 6S PPK equals minimum of USL minus X bar divided by 3S X bar minus LSL divided by 3S. Example, if USL equals 10.2, LSL equals 9.8, mean equals 10, sigma equals 0.05, CP equals 1.33. CPK equals 1.33, 1.33. Good capability and centered. Analogy, like a train arriving on time, 8:55 to 9:05, consistently at 9:00, shows high CP and CPK. Exercise. Calculate CP, CPK, PP, PPK for IT ticket closure data. Eight. Short-term versus long-term capability. This slide highlights how short-term and long-term capability metrics are applied across different industries. In manufacturing, we often use CP and CPK to study consistent product dimensions, like tire thickness, focused on immediate variation and process centering. In IT services, we apply CPK to monitor short-term metrics like first response times to ensure timely support. Banking relies on PPK studies to understand long-term process consistency, such as loan approval cycle times. In healthcare, PP and PPK help assess longer-term patterns like emergency room wait times, accounting for broader process shifts. In summary, CP and CPK show how a process performs in the short term, while PP and PPK reflect long-term capability, factoring in more variation over time.